Hi everyone, this is Dr. Brian MacDonald, author of Practical Stress Analysis with Finite Elements, and today we're going to be doing a plate with a hole using plane stress elements in ANSYS Workbench. So yeah, we're doing the plate with a hole problem. So every course on FEA or every introduction to FEA has the old plate with a hole. So let's take a look and see what we're going to do. So we're going to look at the 2D stress distribution in a flat plate with a central hole loaded in simple tension. So here's our plate here. It's loaded in tension. We're given the various dimensions of the plate. We're given the cross-sectional area worked out here from the thickness multiplied by the height, which is also 0.1 meters. So the square plate 0.1 meters high, 0.1 meters wide, of thickness 0.001, cross-section area of 0.0001 meters squared, or 0.1 of a millimeter. Central hole has a radius of 0.005 meters, tensile load of 1000 newtons. We're told it's made from steel with an elastic modulus of 210 gigapascals, which is 210 by 10 to the power of 9 pascals, and a Poisson's ratio of 0.3. So we're going to take two approaches here. We're going to do what I consider the wrong approach first, which is to model the full problem using 2D plane stress elements. So we're going to make a model that looks like this. It's going to be the entire plate. We're going to hold one side of it. We're going to put a load to the other. And then we're going to do what is the correct way to model this plate, which is we're going to exploit symmetry and just model 1/4 of the plate. And we'll just show that we get the same answer. Now, important thing to realize when you're modeling using symmetry is that if we're just modeling 1/2 of the length over which this load is applied here, then we're going to apply 1/2 of the load. Okay, so the load, not just the geometry, but the load is considered to be symmetric as well. So if we put a symmetry boundary constraint on this edge here, it means that the geometry is mirrored over it, but the load is also mirrored over it as well. So that's a very, very important concept. Symmetry doesn't just affect the geometry, it also affects the loads. So in both cases, we're seeking to find the maximum horizontal stress in the plate, which we will validate against analytical theory with the help of stress concentration factors. So you'll see when I do the full plate why it's actually, funnily enough, a bit more difficult than doing the 1/4 plate. So it creates its own problems, which requires a bit more advanced modeling to get over, and actually the 1/4 plate is the simpler solution. So we'll go through both anyway, and you'll see what happens. So just to get the theory and see what kind of results we're aiming for. So simple stress theory tells us that the stress is the applied load divided by the cross-sectional area. So if we ignore the hole in the plate, then the nominal stress, which is the stress if the hole wasn't there, would be force over area, which is 1000 divided by 0.0001 meters squared, which gives us 10 by 10 to the power 6 pascals, or in other words 10 megapascals. So that's what the stress would be in the plate due to 1000 newtons being applied in simple tension if there was no hole. Well, what about the hole? The hole obviously affects things. So we know that the hole is a stress concentrator and it will raise the stress in the plate. And if I just go back to the previous slide for 1 second, it's in this area here. If you think about this plate and it's been pulled apart, this area here is going to experience the high stress. This is where it wants to tear apart, basically. If we were going to get a rip in the hole, it would occur here and here. Okay, so we're going to get high stresses in that area there. So what the stress concentration factor tells us, it tells us, well, what will the value of the stress be in that location where it's going to be very high. So if you look up stress concentration factors, you will get an empirical curve like this. So by empirical, it means it's derived from experimental results. So on the vertical axis, I have K, which is the stress concentration factor. And on the horizontal axis, I've got R divided by D, where R is the radius of the hole and D is the depth or height of the plate. Okay, so we've got this graph down that shows how K varies depending how R over D varies. Okay, in our case, R divided by D, the radius of the hole divided by the height of the plate, is 0.05. And if we go down here to 0.05 and come up here, you'll find out that this gives us a stress concentration factor of 3. Okay, so the maximum stress in the plate due to the hole then would be 3 times the nominal stress. Okay, so our maximum stress is K, which is 3, times sigma nom, which we worked out to be 10 megapascals. So our maximum stress, according to stress concentration factors, will be 30 megapascals. Okay, and again, you might, okay, first of all, the full graph isn't here, so it doesn't go right back down to 0. So you can find more accurate graphs of this if you just do a quick search on the internet. And you will find that for this ratio, k is always going to be equal to 3. You'll also find an equation describing this graph. So rather than reading it from a graph, you'll actually find an equation that you can work k out depending on r and d and some other values as well if you like, and you will find k is equal to 3. Okay, so with that in mind, let's open up Workbench and get going. Okay, so here I am in Workbench, and we're going to do a static structural analysis. We're going to do the simplest analysis we can. So we're going to click on static structural, pull it over here, and if we want, we can give it a name. Let's call this one plate with a hole. And the first thing we're going to do is go in and check our engineering data. So structural steel is already there, but that's using 200 gigapascals. So let's just make our own steel. So let's just click here and call it again, whatever you like. I'm calling it my steel this time. And my steel at the moment has no material properties. So I go over here, click on linear elastic if it's not already open, and double click on isotropic elasticity, and it populates the table here. I'm just going to set Young's modulus as 210 e to the 9, and I'm going to set Poisson's ratio as 0.3. Okay, so that's my material defined, so I can now shut down my engineering data. First thing I'm going to do here is save my project, so I'm going to go File and Save As. Again, it's a good practice to put your working directory in a directory where you have some space, because as Workbench solves, it's going to write a lot of big matrix files as it solves. So, you know, don't put it on a flash drive or anything like that. It'll probably crash when it tries to solve. So I'm just using the temporary directory on my hard drive. And again, I'm just going to give it a name. I'm just going to call it a 2D plate with a hole. So you can call that whatever you like. I'm just going to go save. Now I'm going to click on Geometry, and you'll see that I get this menu over here. If that menu isn't there, I just right click on Geometry and I click on Properties, and that will open the menu for me. And the first thing I want to do here is change that analysis type. If you can't see it, you may need to scroll up or scroll down. Change the analysis type to 2D. Okay, because I'm going to do a 2D plane stress analysis for this. That's the most appropriate analysis for this type of problem. Now that that's set, I'm going to right click on Geometry and go New Design Modeler Geometry. And I'm just going to wait for the design modeler to open up. Okay, now my design modeler is opened. I want to start drawing my plate geometry. So I'm going to click on XY plane. I'm going to click here at Look at Plane. Again, I'm going to click on Sketching. And if you want, you can come in here and you can set up a grid. So show 2D grid, snap. Just to go back to our problem definition again. So you can see our plate is 0.1 millimeter wide, 0.1 millimeter high, a thickness of 1 millimeter. Sorry, it's 0.1 meter wide and 0.1 meter high, very important, and a thickness of 0.001 meters or 1 millimeter, and the radius of the hole is 5 millimeters or 0.005. So 0.1 by 0.1 first of all. Okay, so back in Workbench, maybe not a bad idea to set the snap equal to 0.1. And again, just make sure my units are okay here. Go up to units. My units are meters and degree. That's fine. So you can see I can't see my grade here. So I'm just going to zoom in. So just zoom right in there. Okay. And now first thing I want to do is draw a square. So I'm just going to draw a rectangle. I'm going to click on the center point. I'm going to pull it out there to there. And again, it doesn't really matter if that's the right size or not, because I'm going to go straight into dimensions, and I'm going to say horizontal dimension, and I'm going to change the selection filter up here to just points. Okay, so I'm going to pick again horizontal. I'm going to pick this point, and I'm going to pick this point and pull my dimension up, and you can see down here it's 0.1 meters. I'm going to do the same with vertical, point and pull that out there. And again, that's 0.1 meters. Next thing I want to do then is go back to draw, and I want to do a circle. So I'm just going to put the circle in the middle there somewhere and put it out. Okay, so that's obviously the wrong size. So first of all, I want to dimension that circle so that its center is in the center of the square that I've drawn. So there's a few ways of doing that. I can put in constraints if I want and say that they have to be, central to each other or midpoint and whatever. I'm just going to do it really quickly. I'm just going to use dimensions. So I'm just going to go ahead and horizontal again. I'm going to pick the center point of the circle. And I'm going to pick that point and pull that down. And it's saying 0.06. Well, I actually want that to be 0.05, so just change it. And just going to do another one, a vertical one, from the center of the circle to that point there. Pull it out there, and that's 0.06. Again, should be 0.05. And then the last one I want to do is the radius of the circle. So I click on the radius and put that there. And it's telling me that R5 is 0.002. Obviously, that's much too big. So I want it to be 5 millimeters. So, okay, there's my geometry. So now when there's my geometry, it's all dimensioned. I can go back to modeling. And I'm just going to expand my XY plane, and so you can see my sketch is there. Okay, so now I'm going to go concept and create surfaces from sketches. Okay, and first thing it says, well, what sketch do you want to use? I just click on sketch 1 and I go apply. Okay, so it's going to use sketch 1 to create that surface. Now I click on generate, and now I have my surface. Okay, so you can see that if I click on my surface, then one of the things that's down here is thickness. At the moment, that's equal to 0. So if you remember, our thickness was 1 millimeter, so let's just put that in, 0.001. So now I have my thickness defined. And if I click on one part, one body, you can see I've got a surface body, and it's giving me the various attributes of that body. It's got a surface area here, it's got a thickness of that, and so on. So there's my geometry ready for my first analysis. So I'll just, always a good point to save that. We can close down the design modeler now, and let's double click on model to start that. Okay, so our modeling FEA modeler is opened. There's our geometry in there. If we want, we can click on an ISO view. Okay, let's just go back to the front view. So our geometry is there. Always a good idea just to click on that. Click on our surface body, and you can see it's got structural steel assigned. So the first thing we want to do is change that to my steel. Okay, so it's the one we defined. What I'm going to do here is I'm just going to go ahead and tell it, so it's a little lightning bolt by mesh, and I'm going to go ahead and say, okay, you go ahead and mesh that. So I haven't told it to do anything with the mesh yet, so let's just see what it does. So I'm not expecting much from this. Okay, so as you can see, that's not a great mesh. Okay, so there's large elements here going down into smaller elements, which is fine, but I don't think there's enough elements in there to kind of capture the level of stress concentration that's going to be in there, and the rapidly changing stress that's going to be in that area there. So stress is going to be changing very rapidly, and we've only got 2 or 3 elements in around that area. What I'm going to do, just to show you how this is not a good mesh, is just to go ahead with this for the time being. Okay, I'm going to come back later and remesh that and fix it. So let's go and set up our analysis then. So I'm in static structural, and the first thing I'm going to do is to apply a constraint to the left hand side. So I right click on static structural, I'm going to insert, and I'm going to put a frictionless support. So insert a frictionless face support to prevent one or more flat or curved faces from moving or deforming in the normal direction. Okay, so in other words, this face here will now, here's my frictionless support, I go apply, so it can now not move in that direction, so in the X direction, but it can move in the Y direction. Okay, so it means the plate's allowed to get thinner, but this edge cannot move in the X direction. Okay, so anything along it can move in the Y direction. It's allowed the plate to get thinner, reduce its height, but it cannot move horizontally. Okay, and then the next thing is let's put a force on the other side. So geometry, again, we're going to pick a line. We're going to go OK, and we're going to change this from vector to components, and the X component is going to be 1000. And the Y component is 0. So you can see we have an arrow there. Okay, so you might think, hooray, we're ready to go. Let's try and solve this and see what happens. And I can tell you now it's not going to work. And we'll talk about why. So this is a good learning experience. So let's go solve. So here we have a warning down here straight away. So okay, solver pivot warnings or errors have been encountered during the solution. This is usually a result of an ill-conditioned matrix. So let's just click on the messages. Here's the first one there. Possibly due to an unreasonable material properties or under-constrained model. That's what actually is going on here. Okay, and if you look underneath, we've another warning. Not enough constraints appear to have been applied to prevent rigid body motion. This may lead to solution warnings or errors. So what that's saying basically is, I've constrained it here and told it it can't move, that this face can't move in the X direction, and I put a load in the X direction, but there's really nothing to stop this moving in the Y direction at all. Okay, so this whole problem, if there's a load applied there, it can slide up and down vertically, and there's nothing to stop it at all. It could keep going forever vertically. Okay, so in order to overcome that, we have to hold at least one point in the model in the Y direction. So what I'm going to do is I'm going to hold one of the nodes, maybe this one here, in the Y direction. Okay, and that will allow the problem to solve. Okay, and this is the reason, or one of the reasons, why we don't use this full model, is because it's actually more awkward. What we have to do to allow this to solve now is if we go back to model and go insert named selection. Okay, so the named selection then, what I want to do is I want to click on a node. So I'm going to click here on node in the selection filter. I'm going to click on either that one or this one. Let's just pick that one for the laugh. So I've just picked that node, and here just go apply. So I have one node, and that's my name selection. So again, let's just give that a name so it's easier to deal with. Let's just rename it my special node. Okay, so now I go back into static structural, and I want to insert one more type of constraint. So a nodal displacement. Okay, and it says, well, what name selection do you want to put it on? I'm going to say my special node. And what do you want to do? And what I want to do is I want to put a 0 displacement in the Y direction. So that node cannot move in the Y direction. Okay, that one there. Okay, so if we click on static structural, I've now got a frictionless constraint here. I've got a load, a force applied here, and this one node here cannot move in the Y direction. So hopefully that should help us to solve this problem. So let's just go solve again. Okay, so now we've gotten a solution. Okay, so let's just get some results from that. So what am I going to look at? I'm going to look at deformation total. I'm going to look at deformation in the X direction. So directional deformation already set to X, that's good. I'm going to look at stress. I'm going to look at von Mises stress, which is a kind of an average stress, a good one to always look at. Always a good one to check yielding as well. And I'm also going to look at stress in the X direction. So I'm going to look at normal stress, and then X-axis is already set here. Okay, so let's evaluate those results. So directional deformation then is telling me that the maximum deformation is 4.9 e to the minus 6 meters, which seems fairly reasonable. The stress then, so the maximum stress is 2.944, so that's 29.44 megapascals. So if we just go back and look at what our stress concentration factor predicted, so you can see here we're supposed to be getting a stress of 30 megapascals. So we're not too far from it. We're not too far from it, but I think we can do better. The other thing is, if we go and zoom in here and take a look at this, if you look at those stress contours, they're quite jagged. Okay, and that's not a good sign of a good mesh. Okay, so that we're really looking for those contours. These are average results, nodal average results. They should be much more smooth here. Okay, so in order to fix that, we're going to remesh the model. Okay, so let's get back out again. What you may find, by the way, when you do this, when you look at your directional deformation or your total deformation, you might find it looks way different shape to this, okay? And one important thing to check when you're doing that is to go to the results bar up here and just take a look at this auto scale here, okay? So at the moment, if I was to look at the undeformed plate, it's that shape. If I look at the true scale shape, it's that shape as well, because this is e to the minus 6 meters. It's very, very small. What Workbench generally does is it auto scales it. So in my case, it's multiplying the results by 1.48 to the 3 to exaggerate them. Okay, so if you watch what happens, so that's an exaggerated display. Okay, so again, maybe just turn on the true scale for the time being, or I could put on 5 times. You see, much more exaggerated. Okay, so Workbench will exaggerate the results generally just to show you what's going on. So I'm just going to put it back to true scale again. Okay, so let's go back in and clear this mesh and do a new mesh. Okay, so we're going to click back on mesh. Now what I'm going to do is I'm just going to keep this one really basic. I'm just going to put a sizing around the hole here. So at the moment we've got about, I don't know, 10, 12 divisions around that hole. Let's put more. I'm going to go insert, sizing. It's telling me, well, what sizing on what? I'm going to pick line. I'm going to pick that line there. Go apply. And I'm going to say number of divisions. And I'm going to put, let's say 30 divisions on that. Okay, so you can see the element size is going to be much smaller now. So now I'm going to tell it to remesh. So generate mesh. So now you can see that I've gotten a much finer mesh in there. Again, you know, I wouldn't be too happy with this mesh. It's very messy looking. But let's just see how this one goes for us, that we've got, you know, a finer result in there. Maybe let's just actually give those lines a bit more as well. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So they've divided in 10. Let's make them a bit better as well. So let's just go again, insert, sizing, and let's just pick all of these lines. I just hold down the control key. I'm going to pick all 4 of the edge lines and apply. And this one again, number of divisions, and I'm going to give them, let's say 15, just to make it a bit, the mesh a bit more dense, a bit finer. So now I'm going to go again, generate mesh. We should get a bit of a, yeah, well, that's a bit better. Okay, still don't like the shape of these ones in here and the way they're, you know, and there's things we could do to fix those, but let's just see how this one goes for us. So the first thing you'll notice is that my special node now doesn't exist anymore because I cleared the mesh and got rid of it. So I need to redefine that. So it's asking us to select that again. So let's just click on node and let's just zoom in here so we make sure we get one right on the middle, as close as we can. Let's just pick that one. Okay. We can zoom back out again. And everything else should be okay. The nodal displacement is applied to my special node. The force is applied to this edge. The frictional support is applied to that edge. Right, let's just go and solve this one and see if we get a better result. So we were at 29.4 the last time for the stress in the x direction. So let's see where we are now. We're at 30.06. Okay, so that's closer than we were. And the important thing is if we go in and take a look at the stress now, if we zoom in here, you can see that those contours still a little bit jagged, but you know, much better, much more smooth, and much more what we're looking for. And they're blooming out nicely from the hole as well. Okay, so that's a much better mesh than we did have before. Okay, so right, that's our analysis of the full plate. So let's go back now and rejig our analysis so we have a quarter of the plate. Okay, so let's close down our solver and let's go back into the geometry. Okay, so here's our geometry again. So I'm going to go back onto sketch 1 and I'm going to go back into sketching, and let's just get this to fill the screen. And now what I'm going to do is I'm just going to draw a line, and I want to draw the line so that I can use it to trim this area. So unfortunately my snap is not doing what I want it to do. Let me just go back and maybe turn off the snap or change it. Major grid spacing is 0.1. 5. Let's change that to 10. Okay, that looks better. So that's just giving, that'll allow me to snap into the middle there. Let's go back to sketching. Sorry, sketching again, and we're going to draw a line, and this time I'm going to draw a line from there up to there, and another one from here to there. Okay. Actually, I'm just going to go back into modeling first, and I'm going to delete the surface first of all. Okay, get rid of that, and it's gotten rid of the line body as well, so we should still have our sketch there. Yeah. Now, I'm now going to use the trim command. So I could just start this all over again and just draw it, but I'm just going to use what's here. So I'm going to go to modify, and I'm going to use the trim command, and I am going to start trimming away pieces of this here that I don't want, and I'm going to trim in there and in there, and okay, and now I will have to again delete some, so I'm just going to click on that one and delete it because I don't need it anymore. That one I don't delete. And again, a lot of these dimensions are redundant now, and other lines as well. I still have a bit of trimming to do up here, so I'm just going to go modify, trim again. If you're finding this bit too difficult, no problem, just go and redraw it. Okay, so what you actually want is the quarter plate like I have here. So now I have my quarter plate here with the radius in there. Again, just for completeness, I can dimension that if I wish. Just to make sure that everything's okay. Probably no harm, just to make sure you have the right dimension. So 0.05, that looks right. Again, vertical, and again, just using points. That one, and again 0.05. And then just to be sure, let's just dimension the radius. And it is 0.005. So everything looks okay there. Okay, so that sketch is fine. Let's go back to modeling. So now exactly the same process again. Create, concept, surfaces from sketch. It says which sketch do you want to use. Click on sketch 1, go apply, generate, go on to your surface sketch, put in the thickness. Okay, and that's us done with the geometry. Do a bit of a save again. So now we have our surface body. Okay, let's close down that. Let's open up our modeler. It says upstream data needs to be reread. Would you like to reread the upstream? Yes, we would, because we've changed things. Okay, and you might get one or two warnings when you open that up. You can just ignore them. We're going to fix all of that anyway. So the first thing with the geometry and the surface body, the material hasn't been assigned. So let's just go in and put on my steel onto that. Now that's got ticks. We don't need that name selection anymore, so let's just get rid of that. Again, the supports and the force and nodal displacement are going to be different, so let's delete all of those. And the other thing with a question mark is the mesh. Again, those edge sizings aren't around anymore, so let's get rid of those. Okay, so now we've gotten rid of all our question marks. Again, let's just start off by letting it mesh it however way it wants, just to see what that looks like. And again, not expecting very much here. So yeah, so that's really not a great mesh. Let's just zoom in on the model there, zoom to fit. Okay, so again, it's just the same size all around. That's not great. Let's just solve it with that again and just see what it looks like, and then we'll go and fix it afterwards. So this time we have symmetry edges, so we have to tell it that they're symmetry edges. So we click on the model and we go Insert Symmetry. And then in Symmetry, we click on that, right click and go Insert Symmetry Region. We click on that edge there, so we want to turn that off from face and make it onto edge. So click on that edge there, and we go OK. And it's saying, where is the symmetry normal? Okay, so what direction is normal to the symmetry? So in this case, it's the x-axis, so that's perfect. We don't want this moving in the x direction. We'll do the same thing again, Insert Symmetry Region. Click the bottom here, Go OK, and this time we want that changed to the y-axis because the y-axis is normal to the symmetry plane here. Okay, so we have our two symmetry regions in there. Into static structural, we want to insert our force. Again, it would be on that line. Okay, and this time in terms of components, and the x component is 500 because remember we only have half the line, and the symmetry means that that 500 is reflected over as well. So not just the geometry. So the geometry will be reflected this way and this way, and the load will also be reflected this way and this way. Okay, so I think we're ready to do our initial solve with this fairly poor mesh. So let's just do that. Have a quick save and then click on solution and go solve. Okay, so let's just take a look at our deformation. Again, it's 2.5 e to the minus 6. So for a linear elastic model, you know, that's with this kind of loading, that's about right. So it's, you know, it's less than a millimeter, much less than a millimeter. Let's look at the stress in the x direction then. So here, you know, straight away we're getting a better result straight, even though we've got, you know, less elements. So it's 30. It's what we're looking for. But let's just zoom in a bit. The contours aren't that great. Okay, I wouldn't be too confident in this because the contours are. Let's pan that up a bit. Contours are quite jagged. Okay, so I'd like to see them blooming and curving a little bit more. So what I'm going to do is I'm going to remesh. Okay, so I'm going to go back to the mesh and I'm going to insert sizing. So the first thing I want to do, obviously, I want more elements along that quarter circle right there. Okay, let's get rid of this pan. Okay, so I'm just going to select that quarter circle there. Okay, so that edge there, and I'm going to go OK. And again, I like to work in number of divisions, so I'm going to say, let's give it 20. Okay, so that's going to be, you know, nicely meshed at that. So let's just quickly look at that. I'm going to do a bit more to this, but just show you the effect of that one. So now you can see that, like, I'm getting a nice mesh there. In fact, that's not too bad a mesh, actually. Let's just take a quick look at that one. I'll just go back and show you maybe one or two more tricks after that. Let's just take a solve of that and see what that gives us. Okay, so our directional deformation, again, total deformation, von Mises stress, normal stress. Okay, let's just zoom in a bit. This looks a lot better. Let's pan that up again. Yeah, so that's looking quite nice. Okay, so that's given us quite a good result. Again, 30.76, you know, it's close enough. Let's just zoom out again. Let's just quickly, if that didn't do what you liked, this mesh has ended up doing what I was going to do next anyway, which is called biasing. By biasing, what I mean is one end of this line has a bigger element size than the other end. So if you look down here, the elements are quite small, whereas if you look up here, the elements are quite wide. If this didn't do it for you automatically, let's just see how you do it. So again, we go back to mesh, we go insert, sizing, and we click on our line. So this, let's say, pick this line, go apply, and we'd say number of divisions again, and again we might have, let's say, 20 divisions. So now you can see they're 20 equally spaced divisions. Now down at the bottom where it says no bias, I'm going to click on one of the biases. So I'm going to click on that one there, second one, which tells it that one end should be bigger than the other. The bias factor tells me how much bigger the other end should be than the other. So I'm just going to say 10. So it'll be 10 times bigger at one end than the other. So you can see there, it's done it the wrong way around. So we have to do reverse bias here. So it's flipped it around for us. So now you can see that it's a big element here, getting slightly less as we move in, and getting quite small towards the end. Okay, and again, you would normally do that in the other edge as well. So again, sizing, apply, number of divisions. Let's go with 20 again. And again, the bias is that one there. Phase, I think we used 10. Okay, so you can see there we've got very small elements slowly, gradually changing into larger elements as we move out. So now we have a lot of edge sizing on that. This mesh pretty much looks like that was done anyway, so it might not change too much. Let's just remesh it and see. Yeah, it's not that different. Okay, in fact, it's a little bit more irregular in there. I could argue the previous mesh was better, but let's just solve this one for completeness. Okay, and let's just look at our normal stress. And again, 30.63. Okay, so still the right answer. And again, just getting right in there to take a look at this, you can see the nice blooming of the stress concentration. Okay, and again, the same with von Mises stress and normal stress. Okay, so that is the end of this presentation, showing you how to model the plate with a hole using ANSYS Workbench. Again, maybe just turning on an ISO view, you can see the thickness of the plate, just to check that, just to make sure your plate geometry looks okay. Going back into Z, looking at the XY view again. Alright, so that's the end of this Workbench tutorial, where we've modeled a plate with a hole, and we've modeled it two different methods. We've modeled a full plate, and we've modeled a symmetrical plate, and hopefully you can see after doing that why using symmetry is better. So first of all, it's easier to apply the constraints. It's also easier to mesh. You've got a lot more control over the mesh. And we should always be seeking to use symmetry anyway, because we're reducing the size of our model and making it faster to solve. Okay, so that is the end of this tutorial. Again, I would really encourage anyone out there to just buy a copy of the book. Or most of the stuff I've explained today via this tutorial is explained in detail in the book. So again, the book can be found on Amazon and all good bookshops and online retailers. Alright, so thanks very much for watching, and we'll see you again in the next one.